Digestion and absorption of fat. Well, first of all, just to get right into it, basically, well, what are fats? Fats are triglycerides. Triglycerides are the triesters of glycerol and fatty acids. They're insoluble in water, but they're soluble in organic solvents. And lipids include both liquid and solid fats. Right. Okay. So the first concept you need to understand is that glycogen which is the store of glucose, is not the desired store of energy. Lipids are the better store of energy. So let's see why that is. Well, glycogen, first of all, it's polar, and therefore 1 gram of glycogen will be bound to 2 grams of water. Because it's polar, it'll attract the water. So therefore it'll be stored hydrously, so with water. Secondly, glycogen is not a concentrated source of energy. It's only 4 kilocalories per gram, so it's not concentrated. And therefore, for these two reasons, it being stored hydrously and not concentrated, is not the desired store of energy. Okay. Instead, lipids are the better store of energy. So let's see why that is. Well, lipids, unlike glycogen, they're non-polar, so they're stored anhydrously, first of all. And secondly, they're a concentrated store of energy because they're 9.4 kilocalories per gram. And for these two reasons, fat is the desired store of energy. So where is fat stored? Well, fats are stored in essentially 3 places, mainly 2, but sometimes in muscle. Okay, so let's have a look where fats are stored. Well, some fat is stored in muscle. Some fat is stored around organs, because viscera means organs, so visceral adipose tissue. And this is associated with obesity and older people. And it's apple-shaped, and it's unhealthy. It puts you at a greater risk of diabetes, insulin resistance, and cardiovascular diseases. So that's around organs, but it's also stored under the skin, and this is called subcutaneous adipose, right? And this is healthier than this, and it'll be pear-shaped body, and an average weight person, 75 kilograms, they'll have 15 kg of subcutaneous adipose fat, which can sustain you for 50 days. Fats also have various uses, so let's have a look at some of them. Well, the uses of fats, they're used in cell membranes, as lipids in cell membranes. They're used for healthy skin, insulation in many places around organs. So that's the visceral adipose around organs, insulation just generally for warmth, and also insulation for myelin. So fats make up myelin for the brain and nervous system. Also, fats are for vitamin absorption because fat-soluble vitamins A, D, E, K. If you absorb the fat from your food, you'll be able to get those fat-soluble vitamins. Also, fats can be used to make hormones. So phospholipids are used to make arachidonic acids, which then become prostaglandins, which is an eicosanoid. Eicosanoids, what are they for? Well, they're for regulating blood pressure, modulating the immune system, and inhibiting sticky platelets, so essentially preventing clotting. And fats are also, they're the energy storage in the fasted state. So therefore they're crucial to health. Just to change that slightly, they're the energy source in the fasted state. They're the energy, their fats are the desired store of energy, as we saw earlier, but in the fasted state, they're the preferred source of energy. So therefore, due to all of these reasons, essentially, the fats are crucial to health. So I said that fats are the energy source in the fasted state. So how do they provide this energy? Well, fatty acids are metabolized by an initial step, and then by beta oxidation, the beta oxidation cycle, and then they enter the citric acid cycle, the Krebs cycle, giving a total of 130 ATP. So let's see how this happens. Well, fatty acids are combined with ATP, so they react with ATP, catalyzed by acyl-CoA synthetase, giving you fatty acyl-CoA. So the enzyme kind of makes sense. You're synthesizing acyl-CoA. That's the initial step, giving you a -1 of ATP because you've used 1 ATP in the first step. Then the fatty acyl-CoA, it enters the beta oxidation cycle. So what happens? Well, when it enters the beta oxidation cycle, it gives you 3 reduced NAD and 2 reduced FAD. And the reduced NAD and reduced FAD, as we know, they enter the electron transport chain, giving you 5 ATP. And because it's going round the beta oxidation cycle 7 times, it's making 7 times 5. So that's 35 ATP. But remember, you use the -1 in the initial step, the preparation step, to make the fatty acyl-CoA. So that gives you 34 ATP from the beta oxidation cycle, essentially, including the initial step. But once it goes through the beta oxidation cycle and it produces the 3 NADH and 2 FADH, you get a fatty acyl-CoA, so the same thing, -2 carbons. So every time it goes around the cycle, it loses 2 carbons, and then it goes back into the cycle. So if you think about it, the longer the fatty acid, the more times it will be going around the beta oxidation cycle, therefore the more energy will be being produced. Eventually, when it goes around the cycle and you're left with, and it's produced all this, you're left with acetyl-CoA. And acetyl-CoA, it enters the Krebs cycle. So it kind of, similarly to the glucose metabolism, glucose eventually becomes acetyl-CoA, pyruvate to acetyl-CoA, then enters the Krebs cycle. So similarly, fatty acids become fatty acyl-CoA, become acetyl-CoA, enter the Krebs cycle. And what this does is it gives us 12 ATP, but it goes round, it produces 8 acetyl-CoA. So 8 acetyl-CoA are coming in, because if you think about it, it's going around 7 times. So it's producing this 7 times, but ultimately each is going to make 8 acetyl-CoA. So 12 times 8, that gives us 96 ATP from the citric acid cycle. So as you can see, they're a very, very concentrated store of energy. So if we get 34 ATP from the beta oxidation cycle and 96 ATP from the citric acid cycle, then the total produced by the fatty acid is 130 ATP. So just looking to summarize that again, fatty acids are metabolized by an initial step, so -1 ATP, beta oxidation, and then enter the citric acid cycle, giving 130 ATP total.